You have an equation of mass conservation, which depends on the density. You have hydrostatic equilibrium, which depends on the mass you get and the density. And so this gives you two equations and three unknowns. The equations themselves are straightforward. If the body is rotating, for example, you might have to add centrifugal force. But typically, the planets that we think about, rotation is relatively small, and that's a small perturbation, not essential to the physics. Okay, so that's part one. Part two is the hard physics. I need to know rho. So I need to have an equation of state. And I don't have to tell people here that that's a difficult calculation to do. Not only that, but the equation of state depends on not only on the pressure, but on the temperature. So I need something to tell me how the temperature changes inside the planet. And that's going to depend on the thermal diffusivity and on the conductivity, on the temperature itself and the material. And it's, again, very difficult physics. And each one of these things is a project by itself. But there's another part of the problem, and that is the philosophy. How do you build your planet? How do you put it together? And the problem is that if you have a preconceived notion of what the planet ought to look like, you might miss what the planet really looks like. And so the tool we've built is a way of getting around this. And let me tell you the story of how it came about. And the story sort of begins, well, first of all, here are different philosophies of planetary structure. So the first person to do real models in the modern sense was a fellow named Wendell DeMarcus back in the 50s. And in 1958, he published a paper on the structure of Jupiter and Saturn. He didn't worry about temperature because everybody knows that Jupiter and Saturn are far from the sun, so they must be cold inside. That's just an example of how your philosophy can take you to the wrong place. So he didn't worry about temperature. He assumed that Jupiter and Saturn were made up of just hydrogen and helium because all he had was equations of state for hydrogen and helium. He realized by matching the gravitational moments that you had to have a core in Jupiter. So he said, well, I don't know what it is, but I have an equation of state for helium. Let's assume it's solid helium. And then he played with the parameters of his model and got some results. But we now know that Jupiter is a lot more complicated. He missed a whole bunch of things. About 10 years after DeMarcus, people discovered that Jupiter was radiating more energy than it received from the sun. And Bill Hubbard realized that that meant that probably large parts of Jupiter's volume were convective. And so he made models of a uniform mixture of hydrogen and helium. That was his background model. But I'll vary the hydrogen-helium ratio in such a way that I'll get as good a model as I can. So again, he limited himself to a certain background model idea and got his results. The next example that I want to give is Reynolds and Summers. Ray Reynolds was a student of DeMarcus, and that's part of the story. He did models of Uranus and Neptune. Audrey Summers helped him with the computing, and they assumed three-layer models, which is pretty standard and pretty common thing. Rock core, ice shell, hydrogen helium envelope. When Reynolds was doing these models already, he was using computers. But DeMarcus and Reynolds, who did his master's with DeMarcus, both did their original work with hand calculators. So that's the contribution of the technology, and I'll tell you a little bit more about that in a second. And then there were models like I did. My advisor, Al Cameron, said, well, we know that Jupiter was made closer to the sun, so it's got to have some ice in it. And Uranus and Neptune are farther from the sun, so maybe they have methane and ammonia. Build models. And so I did something similar, a rock core ice shell, but I had a hydrogen-helium envelope which allowed various ices to mix inside also. And these are just, again, they're examples of the kind of structure that you impose on the planet. And the minute you impose the structure, then you might be missing other things. So I spent a lot of time at NASA Ames working with Ray Reynolds. And so he was like the generation before. He had used hand calculators originally. I used the mainframe. And one time, the two of us were sitting in the office, and a new postdoc had come. He was a student of Hubbard's, so he was the next generation. Mark Marley, some of you may know. And we were sitting and chatting, and I said, I would really like to get out of this framework where you pose a structure. I'd like to look at different functions or something and see where you can go with these models. And Reynolds said, yeah, I had the same idea, but I don't know what function to use. Well, it's not an idea that's been ignored. In fact, Ravit uh, made polynomial fits. And a polynomial is a very nice idea, because what you can do is, if you have n parameters that you observe, you take a polynomial of order n minus 1, and so you have n free coefficients. You pick the coefficients so that they fit all your observations. Now you've got a function that exactly fits everything you see. And then you can try to interpret it, understand it. The problem is that you've only got one such function, and maybe there are other things. So this is a nice idea, and it's in the spirit of what we were looking for, but it's not quite. And then Benno now has been working with polytrope parameterizations, which is, again, something we hadn't thought of. But a polytrope is very nice because it looks like an equation of state. Real materials behave like that. So this is closer to the physics, and that was the idea. What we decided to do at the time, and it was Mark Marley's idea, was to just do random models. Marley had that idea because he was less afraid of wasting computer time than we were. If you're working with a hand calculator, you don't want to try a million random models. And even with a mainframe, it's a problem. But nowadays, it's not such a problem. And so Marley and the student of his, Gomez, and I did a set of models in 1995. We couldn't do very much with it. You had some random functions. About 1 in 1,000 fit the observations, 1 in 2,000. So you had to compute a lot of models, and then you get something, and okay, so then what do you do with it? But it was an interesting problem, and a few years later, when my son Joshua finished high school and was sitting around waiting for his next stage in life, I said, "You like computers? Why don't you do some random models?" And he really did like computers. He's very good at it. So we wrote another paper that he helped with, and then that was the end of the thing. So that was over 20 years ago. In the meantime, Joshua has gotten a real job, and he works for a hedge fund, and does computing, but not this stuff. So he's out of the field. But I'll get back to that in a second. So one of the problems that came up, and this is Uri Malamud, who's the third partner in this project, he pointed out something very interesting. When I had originally done my models, my advisor said, look, take solar composition material, leave out the hydrogen and helium, take the stuff that can condense. What kind of ratio would you expect for water to rock, for example, or rock to water? And you expect 1 to 2. There's a lot more oxygen in solar composition than rock forming materials. So you expect a lot of water. And in fact, most models of Uranus and Neptune looked for that kind of ratio and found it. But Uri pointed out that in comets and KBOs, Pluto, the rock to water ratio is 2 to 1. And you would expect to build Uranus from objects like Pluto. So why doesn't Uranus have a 2 to 1 rock to water ratio? Can it? And then we came back to the idea of, well, I don't know how to build a model like that, but let's look at random models. Can we generate some sort of density distribution that will work? So I got in touch with my son in the US, and he said, yeah, I've been thinking about this for the last 20 years, how to improve the random models. And he came up with some nice stuff, so I'll show you what we do. And he built this tool. Okay, so first of all, what can we observe? Well, obviously, we observe the radius of the body, and we can get the mass of the body. And the mass is a function of the density. So if I can give you a random density distribution, I have to make sure that it matches the mass. That's easy to do. That's trivial. And then what else can you observe? Well, the gravity field. Okay, the gravity field is a problem this is the gravity field, and you can measure these coefficients for, if you're not familiar with it, there's the potential energy. It's like GM over R. And then there's all kinds of perturbations because the planet is not spherical. It's rotating. And so if you just look at the azimuthal symmetry, you get these coefficients Jn. These are Legendre polynomials. Theta is the angle from the spin axis. And then if it has mountains and valleys and oceans and stuff like that, then you can measure these kind of things. That's not relevant for a rotating fluid planet. But you can measure the J's, and you can try to match them. And in fact, that's the relationship that you get. The J depends on the density as a function not only of radius out of the planet, but also of the angle from the spin axis. And the radius and so on, then again, Legendre polynomials and things like that. It's an expensive calculation to do. It's not nearly as expensive today as it was in the old days. And we can do it. We can build our tool to do that, but we decided to choose something simpler. And there are several reasons. First of all, the truth is that it's simpler. But the official answer is that you need to know the rotation rate. I need to know the shape of the planet in order to calculate the J's. And there are two rotation rates in the literature. One is the Voyager period that was measured from looking at the magnetic field and the radio observations, and that's 17.24 hours. And then if you look at the wind speed and the planetary shape, Ravit did this, 16.58 hours, and that's going to make a difference in the J's. So there's a reason, a legitimate reason, not just the being lazy reason, that you don't want to use the J's. So what else can you do? Well, there's moment of inertia. And that's, again, just a simple function of the density. The problem is that moment of inertia is not something that's easily measured. We have moments of inertia for the Earth and the Moon and now even for Jupiter, but we got that just very recently from the Juno data. For Uranus, we don't know. So it's a nice idea. Can you apply it? And the answer is yes, you can. What you do is you measure the shape of the planet, the equatorial radius and polar radius, and you get the flattening. And then there's an approximation, and it's an approximation. So you measure the J2, that gravitational moment, and that gives you sort of an idea of what the moment of inertia is. And it could be off a bit, and I'll show you that later. But it gives you an idea of what the planet ought to look like inside. So that's what we did. Okay, so what do? So you pick a random function, and the random function is simply picking numbers. First of all, let's start with something simple. I'll assume the radius goes from 0 to 1, and I'll assume the density goes from 0 to 1. And I want the density function to be monotonic. I think everybody will agree that that's a reasonable assumption. Okay, so now what I need to do is I pick some random values between 0 and 1, pairs, and that's my normalized density distribution. Then I integrate that to get the mass, and it's going to give me the mass modulo some alpha. I choose the alpha so that I get the right mass. And so now my real density distribution is B alpha times this normalized thing. Okay, now I have a density distribution. Then I want to integrate this density distribution to see that I get the correct moment of inertia. And you rarely do, which is, I guess, not surprising. A random function that gives you that integral won't necessarily give you the correct value for that. Okay. And typically, what we found was like maybe 1 in 1,000 works reasonably well. So there's a trick. But before I do that, let me tell you what the problem is in this. What you see here is I've divided up my range from 0 to 1 to 10 points, 0.1, 0.2, 0.3, 0.4, and so on. And for each one of these points, I pick a random number, and then I arrange them so they're monotonic, and then I get one of these random curves. And just to show you where y equals x is, that's the black line. Okay, so now I have 3 random functions. Each one of these could be a density, and I'll normalize it to get the right mass and so on. And they sort of fill a large region of this possible space, but I don't have anything up there, for example, or down here. I don't have something that's low density and then jumps up. I can get that eventually, I suppose, but this is with 10 points. If I use 50 points, I don't know if you notice what happens. It sort of gets closer to this y equals x curve. And if I use 200 points, it does that. The more points you use, the more chances you are that you'll find something that when you arrange them, that the fluctuations will be smaller, relatively speaking. And if you use 1,000 points or 10,000 points, you just get a straight line or very nearly a straight line. It doesn't help. So you have to be a little bit clever. And that's one of the things that Joshua did. He said, look, instead of picking a random point, 10 or 1,000 random numbers and just arranging them linearly, pick a random number here and a random number here, a pair. It gives you that point up there. Okay, now, divide this space into two regions, one region here and one region there, and pick something random inside that's monotonic. So for example, you get that. And then you do it again and you get that. And you do it again and you get, after many, many points, something like that. That is very much different from the y equals x curve that you see, that I showed you. And these kind of choices allow you to look in all kinds of regions of this parameter space. So that's one trick. Another trick. I find a density distribution that gives me the right mass. I calculate the moment of inertia, and it gives me whatever it gives me. Then I take a second density distribution that gives me the right mass, and I calculate the moment of inertia, and it gives me something else. If C1 is less than what I want and C2 is more than what I want, well, then it's simple. I do that, and I get the right C. And then I do that for the density distribution, and that density distribution will give me the right moment of inertia. It'll also give me the right mass, because both our rho 1 and rho 2 give me the same mass. So automatically, I get what I want. So it turns out 2 is not a good sample to use. You calculate 10 models or 50 models, and then you're bound to get some that are lower and some that are higher, and then you just pick something randomly and match it. And so very, very quickly, you get a random distribution that gives you the right mass, the right moment of inertia. So we're there. And here's, then there's one more thing that you can do. This is a sample of a density distribution that's already been normalized properly. And you see that the radius goes to like 2.5 10 to the 9 centimeters, which is the radius of Uranus. The density is in grams per cubic centimeter here. So it starts off at like 12 at the center and goes down to something close to 0 at the surface. You can smooth it. There are off-the-shelf smoothing routines that you can use to make it smoother. So here, for example, is using a smoothing factor of whatever. I don't remember the numbers here, but you can see that it gets a little bit smoother. I can make it smoother, and I can make it even smoother. And this already looks like, here, this one. It looks like maybe a core with a dilute part of the core and then an envelope, and it sort of begins to look like the kind of thing that you would want to see for a density distribution. And this one works. It gives you the right Uranus. Now, what do you do with that? Okay, so I have the mass. I can calculate the pressure everywhere because I just have to integrate that. And once I've got the mass, I can get the pressure. And I have pressure and density. If I had temperature, I'd be in really good shape. So we have tricks. Here is one algorithm that we use. And this is, well, this part at least has some physics in it. Well, we consider 4 different materials. We can do more than 4, but the limitation is, okay, so the 4 materials in our case are a solar mix of hydrogen helium, which we call envelope, water, rock, which is SiO2, and iron. And we have equation of state tables for all of these. And we allow any 2 adjacent materials to mix. In other words, envelope can mix with water, but not with rock or iron. Water can mix with envelope in the outer part of the planet and with rock in the inner part of the planet, and rock can mix with iron and so on. So we limit ourselves to 2. There are ways of dealing with more than two things mixing. We haven't done that yet. Okay, and the rule is that the heavier material can only increase as you go toward the center of the planet. You can't, for example, go inward and all of a sudden have less water and more envelope than you had outside. So that's a limitation that I think is reasonable, physically speaking. Okay, and then what do we do about the temperature? So for the temperature, we have different algorithms. The one that is most reasonable is this one. I'll show you a few others in a second. You know the temperature, density, and pressure at the surface. That's given. Then you find the composition. X1 is the mass fraction of material 1, X2 mass fraction of material 2, and you want, given the pressure and temperature and the densities of the two materials, you want to be able to match the density that your random function has given you. Okay, I do that. Now I take a step inward, and I know what the new pressure is and what the new density is. So now I say, assume the temperature is constant. No physical reason for that. Assume the temperature is constant. What new mass fractions do I need in order to match the density my random density? If the new mass fraction of the lighter material doesn't increase as I go in, then I'm good. And I just take that and continue to the next step. If it does increase, I say, no, that I can't allow. So I increase the temperature a bit and try again. And I keep increasing the temperature until this fits. And the result of this algorithm is it gives me a composition profile and it gives me a temperature profile, and it maximizes the mass fraction of the lighter material, and it keeps the temperature profile as low as possible. So whether that's physically correct or not, I don't know, but at least it gives me an idea of what can happen. And I can look at models like that. Okay, so here are a bunch of models. What you see here is we ran 100,000 models. About 75,000 of them were good. For numerical reasons, some of them failed. And what you see here is the envelope mass fraction as a function of central temperature. Actually, the other way around, but okay. And what you see, for example, is there's some physically reasonable things. The envelope mass fraction here, as you go to higher temperatures, you need less envelope because you're making the heavy stuff lighter. So you can understand this sort of shape here. It's interesting that there's a cutoff. You can't get an envelope that's more than 40% of the planet. The central temperatures can be quite high. You can go up to 140,000 Kelvin at the center, which is ridiculous. There's nobody would believe that it's really that hot. So what do people believe? Well, classical models give you temperatures of something like 10,000 Kelvin at the center. And classical models, if you would ask me how much hydrogen helium there is in Uranus, I would say something like 3 Earth masses or so. That's maybe a fifth, so that's 20%. So that's right around here. So that's reasonable. Ravit and others have found models that have 20,000 degrees at the center and even a bit more. We decided to do a cutoff at 50,000. That's a very generous cutoff. It almost certainly doesn't get that hot, but that's the region. And here's a close-up of that region. So you can say something about possible mass fractions of the envelope. So that's one thing you can do. This is what we were interested in, the rock to water ratio. And so you see most of the models, again, central temperature here, most of the classical models are in this region, and that's what we get. But you can get values rarely of 2 or even a little bit higher. What I should mention is I'm using a moment of inertia, normalized moment of inertia of 0.23, which is a reasonable value, I think, Everybody will agree. Okay, so this is what you get. In order to get the high rock to water ratio, you need higher central temperatures. And so you don't get 2 until you get up to central temperatures of 25,000 or so. And so that's sort of uh, uncomfortably high, but not crazy high. And okay, and there you go. What do, yeah, there. This is what these things look like. This is the envelope mass fraction as a function of rock to water fraction uh, for models that have a central temperature between 0 and 10,000 Kelvin. And you can see the shape is reasonable. The hotter, the more rock you put in, the more envelope you need to balance it so you get the same mean density. And so that's what you get. You can see that if I limit myself to the temperatures of the classical models, I can't get a 2-to-1 rock to water ratio. But if I go higher, this is up to 20K, and this is 30,000 Kelvin. 30,000 Kelvin already, you're getting out there. And that's 40,000. 40,000, you can find models. And I think I have 50,000 as well. Okay. So that's sort of how these things look. And that's one of the things that this tool can do. It can look at distributions of models and tell you what's possible and what's not possible. Let me show you what some of these models look like in the interior. So here's one particular model. You see the density distribution on the left and the associated pressure. So the density is, I think, pretty high for what I would be used to in classical models, 18 grams per cubic centimeter. And the associated pressure is high too, it's about 14 megabars. And here is the temperature distribution that you get with this. I picked this particular model because it has actually a low central temperature, 6,000 Kelvin. The temperature distribution doesn't look very physical, I admit, because it's got constant temperature and then it drop, and it has these steps. Nothing I can do about that. But I will point out that inside of about 15,000 kilometers, 1.5, 10 to the 9 centimeters, the pressures are a megabar and above. And at those points, the temperature is not that sensitive to temperature. It's the pressure that's giving you the density. And if I would change the temperature from 6,000 to 10,000, even at the center, I wouldn't change the density very, very much. Very, very little, in fact. So I could smooth this out and not affect the results very much. So don't let that scare you too much, but it gives you a feeling. And what you see here is the composition. So you see the mass fraction, the red is the mass fraction of iron as a function of radius, and you see it goes down, and as the mass fraction of iron goes down, the mass fraction of silicates goes up. And then when you run out of iron, then I can mix silicates with water, so the silicates go down and the water goes up, and then the water and the hydrogen helium. So you can see in this particular model, I have at the outer layers, I have a very, very hydrogen-rich atmosphere, almost solar composition hydrogen helium. Tiny, tiny little bit of water, but it increases rapidly as you go inward, and that's it. So you can decide if that makes sense to you or not. The temperatures are reasonable. It fits all the observations, and it's a reasonable model. The rock to water ratio in this case is a half. Solar composition, basically. And this is a classical model. Here's another one. This one has a lower density, 14 grams per cubic centimeter, but higher pressures because it's high temperatures. And the temperatures are not 10,000 or 6,000, but 25,000. So 25,000 already, even the thermal contribution is important. And here, I've got also part of the reason the density is lower is because I've got a lot less iron. I've got only about 55% iron, 45% rock. And you can see how this goes. And here I've got a rather rich outer atmosphere, a lot of water, almost 40%, 35% water, and 65% hydrogen helium. So it's a very wet atmosphere. And in this case, you get a rock to water ratio of 2, which is what we were looking for. You can make a model like this if you believe this temperature distribution, which is, again, I can smooth this out without changing these things very, very much. So you can do it. Are there other physical reasons why this is not a good model? I don't know, but I think some of Ravit's people can contribute to answering that. Okay, so that's the inward algorithm. The outward algorithm starts by a guess at the central temperature and goes outward and tries to keep the composition constant while lowering the temperature. In other words, I take a step outward. I say I keep the composition the same. I'm going to lower the temperature and try to match the density. If that works, good. If not, then I have to change the composition. And you work your way out. This kind of an algorithm likes to keep less water in the planet because it wants to keep the rock the same. And so that's good. That takes us in the direction we want for high rock to water ratios. The problem is that when you get to the edge of the planet, your temperature is 2,000 degrees or something, which is way too hot. So it's a nice idea, but it doesn't work. Then we have the bidirectional algorithm where you look at both the outward and the inward algorithm, and you pick the one that gives you the lower water mass fraction. And so you start off at the outward algorithm, and eventually you just jump down to the lower one and to the inward algorithm, and you get things. I'll show you some results on that in a second. And this, again, gives you higher rock to water ratios, and it tends to give you thicker envelopes also. So let's see what that looks like. Here is a case. Now you've got a density of 22 grams per cubic centimeter and a pressure of 27, 28 megabars. That's, I think, extreme. And here are the temperature distributions that you get from the inward, the outward, and the bidirectional just jumps down to here. So even the inward algorithm wants 20,000 degrees at the center. The outward one, we chose 40,000. And you see, you end up with a surface temperature that's a couple of thousand degrees. So that's clearly physically not right. And then you can use this bidirectional one and make the jump. And again, this jump here is in the high pressure region, several megabars plus. And so the temperatures are not that important in determining the thing. And if we would use a more realistic temperature profile, then things wouldn't change that much. And here are the three composition pictures that you get. So the inward algorithm and the bidirectional algorithm look the same in the inner part of the planet. They have to be. I'm sorry, the inward algorithm and the outward algorithm, no. Again, the outward and the bidirectional start the same at the center. And the inward and the bidirectional end up the same at the edge. And you can see that. But the change in the rock to rock to water ratio isn't very large. It's 1.23 for the inward, 1.21 for the outward, 1.23 for the bidirectional. So all these tricks don't really help. If you want to get a rock to water ratio of 2, it's hard. Okay, so one idea was, well, what happens if you add CO? CO has a density that's sort of between water and silicon dioxide. So it's going to replace some of the water, and it's going to replace some of the silicon dioxide. And if you do it right, maybe you can change the rock to water ratio. And it shouldn't affect the envelope mass fraction. Okay, so we did that. This is without the CO, the same distribution of envelope mass fraction to central temperature, with CO, without CO. And you can see there are differences, but they're small differences. In other words, we're getting the statistics pretty right, I think. But if you look at the rock to water ratio, you find also not very much of a change. Except the interesting thing is that you get when you add CO, you get models where the rock to water ratio is 0. There's no rock. because the CO will do the job for you. So in other words, if you have certain models where you had very little rock to begin with, you can replace all of that with the CO. What happens is, let's see if I can show you this. Here's a particular model, uh, random seed for generating the model. And so you see, again, a density distribution that starts at 14 and goes down to 0, pressure about 14, 15 megabars. Uh, these are the temperatures. So temperature is low for the inward algorithm, 40,000 for the outward. Bidirectional just jumps from one to the other. Again, the outward algorithm gives you a very high surface temperature, so that's not physical. Um, and here is what you get. Okay, let me explain this. Look at the dashed curves. These dashed curves, in particular, the water and the silicon dioxide, the green and the orange. Silicon dioxide, you can see there's the dashed curve. It goes up to nearly 1 and then overlaps with the solid curve. Things don't change in there. So and then the water curve is the dashed orange curve that goes up and then goes out to the envelope, to the outer planet, part of the planet, and it overlaps. You can't see it because it's just covered by the solid curve. Then I put in CO in addition to everything else. And then what happens is the green curve, now look at the solid curves, the green curve shifts to the left because I've replaced some of the SiO2 with CO. CO is the gray curve, the gray peak there. And I replace some of the water, it shifts to the right. I replace some of the water with CO. The problem is that you tend to replace more rock than you replace water. So it was a nice idea, but it doesn't work. And with the inward algorithm, the original model had a rock to water ratio of 1.03, and when you add CO, you get 0.94. So in other words, it works in the wrong direction, and that's universal. It's not just this example, but there are many examples like that. Here's another one. This is using the bidirectional algorithm for the same model, and you can see where the CO sits. The solid curves are with CO, the dashed curves without CO. The only things that change are the silicates and the water. And again, you tend to replace more silicates than you do water, and so the rock to water ratio goes down and doesn't go down very much. Okay, another C, just to show you that it's not just one example. There you see the density distribution and the pressure and the temperatures. And here the temperatures actually differ depending if you have CO or you don't have CO. There's slight changes in the temperature because of the way the algorithms work. But again, not very significant changes. And you can compare here that there's a lot of CO. And you can even see, because of the changes in temperature, you can see the difference between the iron curve, the dashed iron curve without CO, and the solid iron curve with CO. There's a slight difference because of the way that the temperature changes a little bit, but not very significant. Um, and again, you tend to replace more rock than water by putting in CO. And here, in this particular case, the rock to water ratio goes from 0.35 to 0.18 approximately. So you really replaced a lot of the rock and very little of it. Okay. And that's bidirectional algorithm. But you see, then you think about it some more. You say, wait a minute. Suppose I look at the chemistry and I admit that if you're talking about megabar pressures, 100 gigapascal, and thousands of degrees, chemistry doesn't mean anything. So I agree. But maybe somehow when you're forming the planet, uh, the CO would react with the hydrogen and give you methane and water, and maybe that somehow uh, tells you what or affects what's happening, how these things are arranged within the planet. And so maybe we should be using methane instead of CO. Well, CO has a density between silicon dioxide and water, but methane has a density between water and envelope. It's lighter than water. So that's going to change things. It's going to replace the water. It's going to replace the hydrogen helium. But it's not going to touch the rock. So that could work. And in fact, it does. Uh, Here you need to compare the dashed curves, which are without any carbon, and the dotted curve, which is where I put in methane. And you see now you see that the iron and the silicon dioxide stay the same, and I replace the dashed water curve with the dotted water curve. So I've taken out all of this water, and I've put in a lot of methane, and it affects the hydrogen helium also. And then your ratio of water to rock goes from 1.03 to 5.1. And now I can do everything. So I'm ready to hang up my computer and go home. Except, oh, okay, this is another example. Except that there's a problem. If I really believe this mechanism, then the number of carbon atoms and the number of oxygen atoms need to be equal, because the way I get water is just by breaking up CO. So each CO that breaks up will give me a water and a methane. And in this particular case, the C to O ratio is 5.6. So you got to be careful. And with the bidirectional algorithms, even 10.2. Now, there may be other reasons why there's a lot of C in Uranus. I don't say no. I'm just saying if this particular mechanism is the one that's responsible, then you have to be careful. If you believe that cometary material has a lot of carbon or carbides or other kinds of things like that, then it's not impossible to get high C to O ratios. But for this particular model, you have to be careful. There. Okay. Sorry. Uh, Slow to react. There. Okay. So this is the rock to water ratio that we get and the C to O ratio that's associated with it. So you can see if you want to be down here where the C to O ratio is 1, then you're going to get small rock to water ratios. If you allow me to go up to 30 or 50, I can get anything I want. And then this is if I limit myself to C to O 1 or less, because there might have been some primordial water as well. So C can be less than the C to O ratio can be less than 1. And I limit myself to central temperatures of less than 50,000 Kelvin, and this is what I get. So you can see that just at the far right, you get models that are sort of like again, you're not solving the problem completely, but it's interesting. So uh, why do I have to take a moment of inertia of 0.23? If you check it and calculate the J2s, using the Voyager period, the J2s are something like 3.5, 3.6, 10 to minus 3. The real value is 3.5, 3.4, something like that. If I use the Heller et al. Rotation period, I get slightly larger values. But if I were to take a moment of inertia of 0.21, then I've tried the models, and you get something that's low for the Voyager period. You get something that's about right for the Heller et al. Period. Maybe the right moment of inertia to use in these models is like 0.22. I haven't tried it yet, but let me show you what happens when you do 0.21. There. This is color coded, but it's the same idea. It's the rock to water ratio as a function of envelope mass fraction. The darker points are the lower temperature points, and the green points are the higher temperatures. And you can see you can get values up to 3 or so. So it's really dependent on the moment of inertia that you choose to fit. It's easy to get models with rock to water ratio of 2. And so that's it. I think I've concluded. I probably did it in time. Uh, Random models are a fast and powerful way to explore the limits of planetary interiors. You can get Uranus with a rock to water ratio of 2. Whether there are other reasons for eliminating those models is a very important question now. And as I say, talking with Ravit's group, I've gotten a whole bunch of ideas of how one might go about that. There are many, many other interesting constraints and important constraints that you can put on these things. There are caveats. We assume only materials with adjacent molecular weights can mix. That we have a way of uh, dealing with other things. For example, I can put hydrogen into the center, but it's not as neat as this because when you have only two things mixing, everything is fixed and constrained. If you have three things mixing, then you've got a little bit more freedom and you have to deal with that. The thermal profile has no physical basis. I agree. I claim that it's not that important in the interior of the planet, but we are working on a much more physical for an algorithm that is more physically based and involves heat transfer in a real calculation for heat transfer. And so that's going to be put in eventually. The equation of state table that we use for methane needs to be improved. We use the old Sesame table, which has limits on how high the temperature can be and so on. And part of the reason some of these models fail is because we go out of the range of the tables. We haven't really matched J2 and J4. We come close, but you would like eventually to get a real fit, at least for Uranus and Neptune. Uh, and we can do that. In other words, you can use the same idea of matching to the moment of inertia to match J2 and J4. It's computationally more expensive, but doable. And that's it. Comments, suggestions, advice is welcome, and thank you. That's right. Uh, so you're asking me, for example, will water and silicon dioxide mix at high pressures, right? Uh, yeah, I don't know. I don't think anybody really knows. These are the kind of things you have to do DFT calculations for, and that absolutely, absolutely. And if somebody were to do those calculations, say you can't have that much water mixed in with this much silicate, then yeah, okay, we cross out that model. Absolutely. Yes. Hmm. Okay, so that's very interesting. Uh, the fact is that um, I have had been thinking about this non-physical thing, and I was going to generate real profiles. In other words, there are two ways to take this. One way is your way, and I think Ravit actually agrees that this is an interesting thing to do, and it's a simple thing to do. I hadn't thought of it because I was thinking in a different direction, but you're right. Uh, what I had been thinking of was to actually look at the flux, the thermal flux that comes out, and try to generate a profile. Uh, and the problem is with convection, how big is the convective cell? If there's small cells and they have boundary layers in between, you've got a lot of conduction going on. So you need to know conductivity, and so all of that is parameter dependent. Uh, how many cells do you want to believe? What do you think about the conductivity, and so on? Uh, so uh, that was the approach I was going to follow, and we're working on producing an algorithm that will generate a thermal profile without using these guesses. I'm going to impose a thermal profile and then try to calculate the composition. Uh, but your approach is definitely something interesting. And the only reason I'm a little bit hesitant about using it is because suppose you show me that the profile is unstable and I get convection and I mix things and so the composition isn't right. Um, what was my argument going to be? I had an argument. Just a minute. Uh, so I would say that yeah that I don't believe the thermal profile. I would say that I can smooth that profile and still get the same composition gradient. Uh, because if you think about it this way, at high pressures, the pressure at a given density and temperature can be approximated by the pressure at zero temperature plus a thermal perturbation. If I'm at megabar plus pressures, that thermal perturbation is a few percent, not more. And so I can change the temperature by a large amount and still only change the pressure density uh, uh, the pressure density point by a very, very little. And so my argument is, yes, you have a sharp gradient in temperature, but I can make it less sharp and still get the same model. So I'm not sure that that's a good test. And Ravit disagrees. Okay, well, you dare to disagree with your thesis advisor. We can test it. It's an interesting thing to test. Sure. Yes, I think that's a very interesting idea, um, and certainly a very reasonable way to try to exclude things. Um, I'm a little bit concerned that if you don't do all the physics that you need in the evolution models are complicated, and you have certain assumptions. For example, how much convection mixes things. That's a very important parameter here, and I'm not sure that we know exactly how much convection mixes. How much uncertainty is there? Can I still get the model if I change the parameters of the evolution code? So you're right. In principle, it's absolutely good. It would be very interesting to see somebody do these kind of calculations. One of the reasons I'm presenting this material is to get this kind of feedback and to look for collaborations. And so, yeah, I would love to see what happens, but I don't know how final the result would be. But that's fine. You know, intermediate results are good. This is a very intermediate result. Yeah, that sounds like a good way to approach it. Yeah. Mhm. Well, if you notice, all the distributions sort of have a high peak and drop down, and they drop down more gradually or less. And, that's because I'm forcing it to match the moment of inertia. Okay, so that's one very strong limitation on how these functions look. Uh, Otherwise, I don't know. There is no other limitation on them. In other words, you can give me a crazy random function. If you can get it to fit the mass and the moment of inertia, there's no physical constraint otherwise. Yeah, yeah, okay. Oh, for the composition, you mean? Yeah, yeah. For the composition, sure. That depends on the temperature. Absolutely. And again, these temperatures that we get, the temperature profiles are not physical. They're just algorithms to generate numbers. So I really, really, the trouble is that my son, who did all the programming, uh, has three kids at home and a day job, and he does this in his spare time. So I can't press him too much. Not like having a graduate student. Uh, and so I keep waiting, and hopefully he will generate these more realistic profiles, and then I think we'll be better able to understand what we're getting. No, yeah, okay, no, that's coming. That's coming. Okay, yes, in principle, the answer is yes. Uh, in practice, there's so many other complications that Ravit can tell you more about, but one of them is differential rotation, for example. If you have winds and things like that, that's going to affect the higher J's, uh, and not so much J2 and J4. So a J2 to first approximation is sort of the moment of inertia. J4 is a little bit more subtle, and the higher the J coefficient, the higher up in the atmosphere you're looking, really. So then winds become important and all kinds of other things. So it's subtle. You're absolutely right that yes, these will be important constraints when we get there. But mhm. Okay, so I think probably it's not a simple question. The answer, I think the short answer is that it should work very well. I know that, for example, for hydrogen and helium, Dave Stevenson 30 years ago or more uh, looked at that and showed that that rule works very, very well. Uh, the way the equations of state are computed, like for methane at high pressures, it's not methane. It's a carbon atom with hydrogen atoms around it. So it shouldn't be that much of a problem. That's another issue. Uh, well, okay. I don't know the answer. We are we just wrote the paper. We did the calculation for CO. There was no equation of state, so we did the calculation, and the referees on the paper would say that indeed our calculation is leaves something to be desired. Put it that way. But it fits pretty well with more detailed calculations. So I think it's not. In other words, the general results, the trends are okay, and this is just the beginning. We're still trying to find our way.